In the summer of 1978, a 59-story skyscraper in the middle of Manhattan was 9 months away from collapsing, not because of an earthquake, not because of a bomb, because someone, somewhere in the chain of construction, swapped one type of steel joint for another, and nobody checked the math. The building was the Citicorp Center, fourth tallest tower in New York City. It had been open for barely a year. Tens of thousands of people worked inside it every day. Bankers, lawyers, maintenance crews, and pedestrians crossed beneath its raised base on their way to the subway. Hidden inside that steel skeleton, threaded through every floor like a silent fracture, was a flaw so dangerous that a single autumn storm, the kind that hits New York once every 16 years, would have snapped the structure apart like a hinge. And the failure wouldn't be gradual. It wouldn't creak. It wouldn't groan. It wouldn't give anyone time to run. The steel joints holding the building's skeleton together would shear simultaneously, and 25,000 tons of steel and glass would topple sideways across 6 city blocks of Midtown Manhattan. But here's what makes this different from any engineering disaster you've heard. The man who found the flaw was the man who designed the building. He didn't go public. He didn't evacuate the city. He launched a covert operation to rebuild the skeleton of an occupied skyscraper at night, in silence, while a hurricane tracked directly toward New York Harbor. This is the story of how a budget shortcut, a student's thesis question, and a 400-ton block of concrete became the only thing standing between Manhattan and the worst structural disaster in America. The problem started not with an error, but with a deal. In the early 1970s, Citicorp, one of the largest banks in the world, wanted to build its new headquarters on a full city block in Midtown Manhattan at Lexington Avenue and 53rd Street. But there was a problem. The northwest corner of that block already belonged to St. Peter's Lutheran Church, and the congregation wasn't selling. So Citicorp proposed a compromise. They would demolish the old church and build a brand new, modern St. Peter's directly underneath the skyscraper, free of charge. The church gets a stunning new sanctuary. Citicorp gets their tower. But there was one non-negotiable condition. The church had to be freestanding. It could not touch the skyscraper. The sacred space had to remain structurally independent from the corporate tower above it. Now, think about what that means. The building couldn't rest on corner columns. The entire weight of a 59-story, 25,000-ton steel tower had to bypass the corner of the lot entirely. The architect, Hugh Stubbins, turned to structural engineer William LeMessurier, one of the most respected in the profession, and asked him to solve what was essentially an impossible geometry problem. Build a skyscraper that floats above its own foundation. LeMessurier's answer was radical. Instead of columns at the 4 corners, he placed 4 massive columns at the center of each side of the building, 72 feet in from the edges. The entire structure would rest on these 4 stilts, each rising 9 stories tall, with the corners cantilevered out over empty air. It was visually stunning, structurally unprecedented, and it created a problem that would nearly destroy everything. A tower balanced on mid-face columns, instead of corners, was far more susceptible to lateral wind forces than any conventional skyscraper. LeMessurier needed a way to stiffen it without adding excessive weight. His solution was a series of massive inverted V-shaped steel chevrons, diagonal braces running in stacked zigzag patterns down the exterior, transferring wind loads through the diagonal members and into the 4 central columns. Elegant, efficient, and it worked beautifully on paper. To handle the increased sway, LeMessurier added one more innovation, a tuned mass damper. Near the top of the building, engineers installed a 400-ton concrete block, roughly the size of a small house, floating on a thin film of pressurized oil. When the wind pushed the building one way, hydraulic pistons drove the block the other way, counteracting the momentum. first tuned mass damper ever installed in a skyscraper. It cut sway by nearly 50%. The building opened in 1977 to rave reviews. It was celebrated as one of the most innovative structural designs in American architecture. LeMessurier became the subject of university lectures. Students across the country studied his chevron bracing as a textbook example of creative problem-solving. One of those students was about to ask a question that nobody in LeMessurier's firm had ever thought to ask. In the spring of 1978, Diane Hartley, an undergraduate at Princeton, was working on her senior thesis, a study of the Citicorp Center that combined architecture, urban planning, and civil engineering. Her advisor was David Billington, one of the leading scholars of structural art. As Hartley analyzed the chevron bracing, she asked a deceptively simple question. What happens when the wind doesn't hit the building face on? Now, here's the thing. In the real world, wind almost never strikes a building perfectly perpendicular. It swirls between adjacent towers. It comes from angles. And the most dangerous scenario is something called a quartering wind striking diagonally, at roughly 45 degrees to the corner. Think of it this way. Push a bookshelf from the front, and it stays put. Push it from the corner, it tips immediately. That's what quartering wind does to a building with no corner columns. And LeMessurier had never checked. In 3 years of design, review, and construction, nobody had ever run the numbers for diagonal wind. Hartley's question traveled from Princeton to LeMessurier's office. When he sat down to calculate the stress a quartering wind would place on the chevron braces, he found something that stopped him cold. Under diagonal wind, stress on the building's joints increased by 40%. That alone was alarming. But it wasn't the fatal discovery. The fatal discovery came next. During the original design, LeMessurier had specified welded joints, continuous connections that fuse steel members into a single, unbroken piece. But during construction, the contractor Bethlehem Steel had substituted bolted joints instead. Bolts are cheaper, faster to install, and in many applications, perfectly adequate. Not here. Bolted joints resist force through friction. Under static loads, they hold. But under dynamic loads, forces that oscillate and pulse with the wind, bolts slip. They loosen. And under extreme shear, they snap clean through. LeMessurier's firm had approved the substitution. It had been reviewed, signed off. But no one had recalculated the dynamic wind tolerances under quartering loads with bolted connections. When he finally ran those numbers, the result was catastrophic. A 70-mile-per-hour quartering wind, a storm that hits New York once every 16 years, would shear the bolts instantaneously. The diagonal members would disconnect from the columns, and without the chevron bracing, the 25,000-ton tower would begin to lean, toppling sideways across Midtown like a felled tree. LeMessurier now faced a decision that no engineer in history had ever had to make. The flaw was entirely traceable to his own project, his own approval chain, his own oversight. And the hurricane season was approaching. He could have stayed silent. Think about it. The probability was on his side. A 70-mph quartering wind might not hit for years, maybe decades. He could have gambled on weather and retired before anyone noticed. Every skyscraper you've ever walked into was approved by a system that, until 1978, didn't even account for wind hitting a corner. He could have hidden behind that code. Instead, in June 1978, he picked up the phone. He called the head of Citicorp's real estate division. He explained the calculations, and he told them the building could collapse. Citicorp authorized emergency repairs under one condition: absolute secrecy. If the public learned that one of New York's tallest skyscrapers could fall over in a storm, the fallout would be devastating. Mass panic across Midtown, a stock crash, lawsuits, a crisis of confidence in every tall building in the country. So the repairs happened at night. Every evening after the last workers went home, carpenters built plywood enclosures around the compromised joints to muffle the sound and conceal the work. Then welders, specialists brought in from across the Northeast, began welding 2-inch thick steel plates over every bolted connection in the Chevron bracing. More than 200 joints spread across dozens of floors, each requiring precise multi-pass welds. By dawn, the plywood was dismantled, the sparks swept clean, and the building opened for business as if nothing had happened. Nobody knew, but the city did know, at least in part. LeMessurier had quietly contacted the Department of Buildings. He had briefed the mayor's office. He had worked with the Red Cross to develop a 10-block evacuation plan covering roughly 200,000 people, one that could be activated in under 2 hours if a major storm hit before the repairs were finished. Emergency generators were installed to keep the tuned mass damper running, because without city power, that 400-ton concrete block was the building's last line of defense. And then, in early September 1978, the Weather Service issued a warning. Hurricane Ella was forming in the Atlantic, tracking northwest toward New York. The welders were halfway through. Ella was 3 days out. The repair crews worked faster. Welding shifts went from 8 hours a night to 12. Additional teams were brought in. The Red Cross finalized its evacuation protocols. Emergency shelters were designated across the Upper East Side and Midtown. For several days, the city of New York had a fully operational disaster plan for a building collapse, and the 8 million people living around it had no idea. And then Hurricane Ella turned. It veered east, out into the open Atlantic, and dissipated without making landfall. By October 1978, every single joint in the Citicorp Center had been reinforced. The building's structural integrity was restored, in fact, improved beyond its original design specifications. The tuned mass damper kept running. The tower stood as strong as LeMessurier had always intended it to be, and nobody outside a small circle of engineers, executives, and city officials knew it had ever been in danger. Here's the part that almost defies belief. The entire crisis, from discovery to resolution, played out during a New York City newspaper strike. The Times, the Post, the Daily News, none of them were publishing. Investigative reporters weren't prowling construction sites. Nobody noticed the welding crews entering the building after dark, night after night, for 3 months. The story, by sheer coincidence, fell into a complete media vacuum. It stayed there for 17 years. In 1995, journalist Joe Morgenstern published the full account in The New Yorker. The article, The 59-Story Crisis, became one of the most widely read pieces of engineering journalism in history. It revealed how close Manhattan had come to a catastrophe that would have dwarfed any natural disaster in American urban history. LeMessurier's reputation remarkably survived. He had come forward voluntarily. He had risked his career, his firm, and his professional standing to fix a problem he could have quietly ignored. The engineering community recognized his actions as a model of professional ethics, a case study, not for the failure, but for the response. His willingness to self-report became a foundational lesson in engineering ethics courses around the world. But the deeper lesson isn't about one man's courage. The deeper lesson is about what happens when cost optimization enters the critical path of a structural system. The bolted joints weren't installed by mistake. They weren't negligence or sabotage. They were a deliberate budget decision. Bethlehem Steel substituted bolts for welds because bolts were cheaper, faster, and easier to install. And under the loading conditions, the building code required engineers to check perpendicular wind only. The bolts were adequate. They passed every inspection. They met every standard. The problem was what the code didn't require. In 1977, the New York City Building Code did not mandate analysis of quartering winds. Engineers were only required to calculate wind loads hitting each face head-on. The diagonal case, the one that actually governs the behavior of a building with mid-face columns, simply wasn't part of the regulatory checklist. And this is the pattern that shows up in every systemic failure this channel has ever explored. The code said check A, nobody checked B, The disaster lived in B. Value engineering. That's the industry term for making something cheaper during construction. In this case, it nearly turned a skyscraper into a tombstone, not because the engineers were lazy, not because the contractor cut corners out of malice, but because the system assumed that if you checked the boxes, you'd covered the risks. It hadn't. The substitution was legal. The approval was documented. Every box was checked, and yet the building was 16 years of weather away from falling over. The system didn't fail because someone broke the rules. It failed because the rules didn't describe reality. Every modern skyscraper built since the Citicorp crisis includes quartering wind analysis as standard. The building codes were rewritten. The profession adopted new guidelines for reviewing contractor substitutions, and value engineering acquired a permanent asterisk. Any substitution must be re-verified against all loading conditions, not just the ones the original design checked for. The Citicorp Center still stands today. It's been renamed 601 Lexington Avenue. The Chevron bracing is visible from the street, those dramatic diagonal lines running up the facade. Most people who walk past it every day have no idea that those steel members were, for 3 months in 1978, the weakest links in a chain that held a city's safety in the balance. There's something deeply unsettling about the Citicorp story, something that no amount of engineering analysis can fully resolve. The building code was followed. The contractor was qualified. The engineer was brilliant. The design was innovative. Every institution in the chain, the architecture firm, the structural consultants, the steel fabricator, the city inspectors functioned exactly as it was supposed to, and the result was a 25,000-ton structure balanced on 4 stilts, held together by bolts that couldn't handle the wind. The gap between what the system checked and what reality demanded was filled by a single student's curiosity, a thesis question, a what if. Diane Hartley didn't know she was saving lives. She wasn't trying to expose a scandal or challenge an industry. She was writing an undergraduate paper about an interesting building. She asked a question because she was trying to understand how the structure actually worked, not how the code said it should work, but how physics would treat it when the wind came from the wrong angle on the wrong night. And that question traveled from a seminar room in Princeton to a phone call with the most respected structural engineer in the country. From there, it traveled to a boardroom in Manhattan, and from that boardroom, it traveled to a welding crew working 12-hour shifts through the night, racing a hurricane up the Atlantic coast. The margin between safety and catastrophe wasn't a wall of steel or a line of code. It was a question nobody in the profession had thought to ask until a student, unburdened by expertise, simply asked it. If you want to keep exploring the invisible systems that hold civilization together and the moments they almost didn't, subscribe to the channel. There's always another failure hiding in the math.